Hi everybody, today we're going to talk about regression or regression analysis, also known as simple linear regression, ordinary least squares regression. There's a few different names, OLS regression, short for ordinary least squares, but no matter what we call it, we're going to dive right in. So a little bit of an introduction, and again, regression analysis, but also known as ordinary least squares regression. Regression analysis we use to see if you have to have a relationship between two variables, and we're seeing if we can predict the value of the dependent variable based on the value of at least one independent variable. We can go on, you'll see in a minute, we can have multiple independent variables, but mostly we're going to focus just on your basic, which is one independent, one dependent. So can the independent, if we know the value of an independent variable, are we able to predict the value of the dependent variable? Regression analysis is also used to explain the impact of changes in an independent variable on the dependent variable. Kind of a little bit of saying the same thing but worded a little differently. The dependent variable is the variable that we want to explain, or also known as an outcome variable. It's what we're trying to guesstimate or predict. Our independent variable is the variable that is used to explain the dependent variable or predict the dependent variable. So we've touched on this before, but keep in mind there are assumptions that we need to make when there are certain assumptions we need to meet when we're running a linear regression. We assume that the distribution of the errors is normal, or the distribution of the variable population data points are normal. That the probability distribution of the errors has constant variance, that the error values are statistically independent, that they are normally distributed for any given value of x, and that the underlying relationship between the x and y variable is linear. And this one's pretty critical. If we don't have a linear relationship, we should definitely not be running this. And as always, it's never just simple with statistical analysis. There are lots of different types of regressions that can be run. So what you learn in most classes, and to start off, is your simple linear regression that has one dependent variable, which is continuous, and one predictor or independent variable, which is also continuous. A multiple regression is one dependent variable with two or more continuous or categorical variables as the independent variables. So you have multiple independent variables. That's where you are always going to start with regression. There are lots of other types. We can do a binary logistic regression, which is what happens when we have a categorical dependent variable and one independent variable, or a multivariate logistical regression, which has a categorical variable of three or more groups for the dependent variable, and for the independent variable, one or more continuous. So we can keep going. There are actually another few other than this, but these are some basic ones, and this is something good to keep and look back on if you've got your data and you're trying to figure out which one to run. This might help. But for the rest of this lecture, we're going to be talking, I believe all, but maybe just 95 at least % of the time, about simple linear regression, or just running a linear regression, basic simple regression, OLS regression. So the model for the simple linear regression is that we have only one independent variable, which we call x, and we're looking for, there is a relationship between x and y, and it can be described by a linear function. And the changes in y are assumed to be caused by the changes in x. Now, correlation, as we know, just tells us there's a relationship. Correlation is not causation. I'm sure you've heard that now 100 times if you're dealing with me on a regular basis. But with regression, we're getting into where we're starting to show that one has a cause on the other, or an effect on the other. We use a regression line when we're running a regression, and this line is the best fitting line, also known as the least squares line. And what it does is it's going to be drawn through the middle of the data in such a way that it is resulting in having the the least amount of error between the actual value and the estimated value. I'm going to show you a picture of this in a second, but it's the closest to as many points as it can get. This regression line gives us a regression equation, and we can use this to predict the dependent variable from the independent variable. And when we talk about predicted values of a dependent variable, they're known as the dependent variable hat, or the dv hat, or the y hat, also known as the y hat. And that little looks like the roof of a house right here. That is what is called a hat. So this is a hat, and it means predicted. So if I say my y value is 5, then my y value is 5. If I say my y hat is 5, then that means that that 5 was derived from something that was calculated, and it's predicted to be 5. Like I said, we're going to do this after we get our regression equation, which comes from the regression line. And that is a mathematical equation that describes the regression line. So let's take a look at this. So these green points are data points, and these are the same two figures. The green points are the data points, and these little dotted lines are showing the least amount of distance to the line. So the least distance from where the point actually is and where it would be on the line. If we took one line and we were to put a line up here, that would not be the least. We have a lot more distance between the points than this imaginary line that I drew up top. This line fits in the middle so that it has the least, and that's the line is created from where the data points are so that it gets us to the least amount of distance between the prediction line or the regression line and the actual data points. And what we can do with this once we have our line is, let's say that we have a point. If we know what our x value is, if our x value is roughly a 1.6, then we would say, okay, then our y value we predict would be roughly 1.9. So we can use this to sort of predict what our y should be according to the way that all the data has been plotting out. The regression equation, as stated earlier, is the mathematical equation that describes the regression line. It is the equation that represents the relationship of x to y in the form of a linear equation. And it's telling us a value for x can be inserted to solve for y. So we use this equation so that we can make predictions for what our y might be. So we write our regression equation as y hat equals b naught, N-A-U-G-H-T, b naught, plus b1 times x. Again, y hat equals b naught plus the b1 of x, or times x. And that is our regression equation. Now, the y hat is going to be the predicted dependent variable. The x is the independent variable. The b naught is our inner slope, or constant, of the regression line, and it's the b naught. And the b1 is our slope of the regression line, or b1. So the very first thing we want to do whenever we're running a regression analysis is we want to look at our correlation scores. These are going to be produced when you run your regression, so they're going to appear. But we need to look at them first, because if we don't have a proper correlation, we don't have a linear relationship between the two variables, then we shouldn't be running the regression. So for this one, we looked at the math scores and the reading scores. We have our mean, our standard deviation, and our count. We have 205 with a mean of 83 for reading scores and standard deviation of 9.9. Our math scores had a mean of 77.4, standard deviation of 10.4. We run our correlation. We ran a Pearson correlation because they're both continuous variables. And we look here, we have our reading scores aligned with our reading scores aligned with our math scores. And we see that our R value is a 0.591. What does that tell us? We know this because we have locked correlations in. But that tells us that we have positive and moderate to moderately strong relationship. But before we determine that there is a linear relationship, the most important thing we want to do is we want to look at our p-value, our alpha. With our alpha level set at 0.05, we want to make sure that this is below 0.05 to be significant. And we can see from our significance that it is significant. It's smaller than 0.001. So we do have a significant linear relationship between math scores and reading scores. And we can write this up. Math scores had a significant positive correlation with reading scores with an N of 2.05 equaling 0.59 with a p-value of less than 0.001. The relationship between one's reading score and math score is a strong positive relationship with an R-squared of 0.35, indicating that 35% of the variance in one variable can be explained by the variance in the other variable. I left out a word there. Sorry about that. Now let's see what this looks like. First, let's look at the regression line. After writing the correlation, we have a scatter plot, and the scatter plot's going to tell us where each and every data point from our data is. So this data point right here is a person that scored roughly 63, 64 on their math score and 53 on their reading score. This person scored roughly 80 or 81 on their math score and 96 or 7 on their reading score. Each of these points is a data point that plots the person's math score and the person's reading score. And we can see, and we talked about correlation, there's a slight cigar shape that's forming in this direction because we know that it is positive, but we could have figured that out just from looking at this, that it would be positive. So what are we going to do? We're going to add that regression line that I've talked about. The regression line has the least amount of space distance from the actual value to the regression line, and this is known as the error. So it has the least amount of errors. There is a calculation for this that is discussed in some other lectures, and we're not going to get into the calculation of it. However, this is our regression line. Now, take notice and always be sure and read your figures and your graphs well. This does not go to 0. This point is not 0, 0. It starts at roughly 58. If this axis were to go all the way to 0, 0, it would be out here somewhere. Let's say out here. This line would continue at this downward slope, and it would enter the y-axis a little bit lower. It would be down here somewhere because it would continue at this angle. It would enter down here somewhere. That's our constant, and these are the numbers that we're going to get from our regression equation. So let me go a little bit farther and I'll show you this, and then I will pop back to this slide so that you can see what I'm talking about. If we wanted to write this up, we could, and I'm not going to spend too much time on writing it up because we're going to break it down in our next slide, but this is how we want to write it up. The first thing we want to do is we want to confirm that we did find a significant linear relationship, and we want to present our R, or our correlation coefficient. We want to always present our descriptives, which is right here, which are right here. We have our reading score mean and standard deviation, and our math score mean and standard deviation is the independent variable. The regression equation we always present. This is very important. And here's our regression equation. Our y hat, this is our b naught, the value of our b naught. This is the value of our b1, and this is our x variable. And we're regressing the x on y. We want to know if it's significant, so we're going to look at an ANOVA to see if it's significant. And the results did indicate that they were significant, that for every 1 unit increase or 1 point in math score that goes up, there's a 0.56 unit increase in reading score. and that math score was a significant predictor of the reading score. And in this, we're going to look at a t-test of our beta for our math score. Now, I'm going to break all this down for you, so don't get overwhelmed by this slide. But here are the things we are going to look at. We look at an ANOVA to see if there's significance in the regression equation, if the regression equation is significant. We look at, to find our degrees of freedom for our T or our R, we find those in the residual degrees of freedom from the ANOVA. And we also want to be sure to include the regression equation whenever we're writing a results section for the regression. As you can see, I have it right here. This is the regression equation. It's the variable equals the B0 plus the B1 plus the X variable. So the Y hat, or the Y predictor, the dependent variable predicted, but we write it out in our actual words. We don't put Y prediction or Y hat and X. We actually plug the variables in. So let's actually write this up, and it's not going to be as bad as you think. And we've got it color coded, so score. Okay, same exact words. It's a copy and paste from the slide before. After confirming a linear relationship, and this is our R, or our correlation, which we have right here. You can see right here is my 0.59. We can see here that my degrees of freedom I find in my ANOVA residual, 203, and less than 0.01. That is also, well, I actually forgot to copy that one, but it is significant because if you run the, I was on the end and I apologize. When you run the correlation, it did show 0.001. And you all know how to write that up. I don't even need to do it again. This is where we get our descriptors. Our descriptive statistics are in this box, which that one we should absolutely know how to do. So after confirming a linear relationship, a regression analysis was run with reading score descriptives as the dependent variable, and math score, with our math score descriptives, as the independent variable. The regression equation, and here's where we're going to plug in our information. We have reading score hat, and we have that there because reading score is our dependent variable. And we want to know where we're getting this. Well, this is our constant. This is 39.772, which I just rounded off to 39.77, plus our unstandardized math score coefficient, which is 0.56. So I'm going to put 0.56 right here, and that is for math scores. And we are regressing reading score on math score was significant, and we want to look at our ANOVA to make sure that this is significant. So I'm going to go over here, I'm going to look at my ANOVA, and we've written up ANOVAs before, so now we're just plugging it in as something that's validating parts of our regression. So the ANOVA with the degrees of freedom of 1 and 203 equals 108.892 with a p-value less than 0.001. Our math score is a significant predictor of reading score. So we're showing right here, this beta coefficient, this unstandardized coefficient, is actually a significant predictor. And we're using our t-score, our t-value, to validate or confirm that it is significant, and it's less than 0.001. These results indicate that for every 1 unit increase in, which is 1 point, in math score, there is a 0.56 unit increase in reading score. This research would reject the null hypothesis that math score is not a significant predictor of reading score. So this screen, you should be able to plug in other regression analyses that you run, and it should help quite a bit. But first, let's go back to the scatter plots. And remember how I was talking about if this regression line had been going all the way, if our x-axis had gone all the way to 0, this would come in right about 35, 40, something if you're just looking at the angles. And that is what we see when we look at our constant, 39.7. and that's our constant. So that's where that line would have crossed had it have gone all the way to 0. That's our constant. So the constant is where the value of y if x is 0. Now, the really, really special thing about regression analysis is we're not always done at this point, because we say that we can predict things. So let's apply it. Let's take that regression equation and use it for what it's intended and try to apply some numbers. So, can we predict the reading scores of two students' reading scores based on their math scores? Person 1's math score is 80 and person 2's math score is 90. So what's our research question, or what's our question we're trying to solve, our answer? If a person has an average score of 80 for their math score, what would we expect or predict to see for their reading scores? And if a person has an average score of 90, what would we expect to see? So person 1, well, here is our regression equation. Reading score hat equals the constant of 39.77 plus a slope of 0.56 on math score. So we plug in our math score of 80 and we just plug it right in there, and we go, okay, reading score equals 39.77 plus 0.56 times 80. Let's multiply out 0.56 times 80. We get 44.8 plus 39.77 is the reading score hat. So the reading score hat, or the predicted reading score, is 84.57, which is 39.77 plus 44.8. You just plug in the numbers and you calculate it. So when we plug in 90 over here, we can see that then we multiply the 90 times the 0.56, we get 50.04, we add it to the 39.7, and the reading score hat, or the predicted reading score for a person with a math score of 90, predicted reading score is 90.17. And that is how it works. So we can go back in and we can predict scores. We can apply what we understand with a regression analysis. If we have our x value, if we have our independent variable value, we can apply it to determine or predict what our y value should be. That is a regression analysis in a nutshell.